So I'm at Tilley, I'm a graduate student at the University of Washington working with the VPL, and recently we did a project to see if we could constrain anything about Proxima Centauri b looking at the auroral emission, specifically the 5577 green line, which you can see here, this beautiful image. So our little review about aurora, they are driven by star-planet interaction. Typically you have some forcing from the stellar wind or a transient activity, like what you see here in this cartoon, which compresses the magnetosphere, energizes particles, and causes a lot of interesting physics. But what you get in the end is the precipitation of particles down into the atmosphere along the magnetic field, and forms these beautiful bands of color, and and forms this auroral oval that this characteristic oval that we're used to seeing. And so in general, I want to point out that we are looking for aurora, not airglow. So we're looking for these discrete, localized, and intense emissions coming from the planet. We don't care about airglow. It's a little too faint. By our calculations, there's no real chance to see that, at least with present instruments and probably with future instruments as well. So we want a really good star-planet contrast. Luckily, Proxima Centauri b is an M dwarf, so it's beneficial to look in the optical region if we want to see something from the planet. So the HARPS data you can see here. Yes, here, shaded in blue, if you can actually see that, is right in the middle of the optical where Proxima Centauri actually has, Proxima Centauri actually has very low flux, and so we're going to look for the 5577 oxygen line there. And it's really exciting if we could see these lines, because not only would it provide an independent verification of the planet itself, it would also help to constrain orbital parameters as well as be a direct verification and identification of an atmospheric species. So that would be very awesome, whether it's oxygen or nitrogen or hydrogen or whatever. It would be a nice direct observation of the atmosphere. So in general, I'm going to tell you how we estimated the signal strength, how detectable we think those signals are, and then about the search through the available HARPS data, the discovery data. So for the signal strength, we use two separate models. So one is just a simple kinetic forcing model, and the second is an empirical MHD fit model by Wing et al. 2014, both of which miss a lot of magnetospheric physics, but they should be just good enough, close enough to a nice order of magnitude calculation for the auroral emission. And so you can think of the magnetosphere as basically an obstacle in the fluid flow of the stellar wind. It has some cross-sectional area that is upon which the stellar wind will impact and dump energy. And so the stellar wind has some kinetic energy, and so therefore you can calculate simply the power dumped onto the surface of the magnetosphere. However, only a fraction of that power is then transformed into electromagnetic auroral emission, which you can see here for Earth. It happens to be about a 1% efficiency on average. And only about 2% of that is the 5577 green line. And actually, that's a pretty big percentage for a single line, but only about 2%. So this is a very simple kinetic forcing model, which we can use. And this gives us a value of approximately 40 to 50 gigawatts for the output of just this 5577 green line, which is about 70 to 80 times that of Earth. Okay, so fairly bright. The second method I mentioned was Wing et al. 2014, this horribly ugly nonlinear equation here. They used a 3D global MHD model to fit the magnetopause surface and across a wide range of stellar wind parameters, and then and then validated it against satellite data, magnetospheric satellite data, to get an empirical fit to make sure that it's empirically correct. And you can see that it has the kinetic portion contributed by the stellar wind, but it also importantly includes the magnetic power that you're convecting onto the magnetosphere. Both includes the magnitude and the orientation of the field, which are important because you must take into account the pointing flux entering the magnetosphere as well as the orientation of the field, which can drive energetic reconnection events, both of which can affect energization of particles and auroral precipitation. So we followed their lead and found a few empirical measurements of, say, electron populations and how they relate to the brightness of the 5577 green line, and tried to determine as close to data as possible what we would actually see. And this is what we find. So for the quiet version, meaning we have no stellar activity and no geomagnetic activity occurring, it matches pretty well with just a simple kinetic model. Including geomagnetic substorm activity, which we use a proxy basically with just assume very strong reconnection at the magnetopause. In reality, the geomagnetic storms have strong reconnection at the magnetopause. They drive a strong ring current, which effectively weakens the magnetic field of the planet and can affect the auroral activity. But you see here we jump up to 140 to 240 gigawatts or so for the green line. Including the effects of stellar activity. This is a coronal mass ejection, say, an order of magnitude greater density in magnetic flux, and a factor of 2 or 3 higher speed in this ejection of energetic particles out from the star. We jump up to 4 to 8 terawatts, And then if you assume that one of these coronal mass ejections actually drives substorm activity on the planet, we jump up in the tens of terawatts. Okay. So again, missing a lot of physics, but a decent order of magnitude estimation. And so this ends up being on the order of tens of thousands of times Earth's nominal 5577 emission for low to moderate geomagnetic activity. So it looks pretty good. It looks fairly promising. I mean, relatively anyway. But let's actually talk about detectability. This is the line here on the right. This is a nice high-resolution spectrum we produced for Proxima Centauri b as viewed from Quadrature. You can see the green line here that we injected. It's a 0.1 terawatt, so it's the lower end of our estimations that I just showed you. And it has pretty high flux density, so that looks promising. However, it's an extremely narrow line, and so the effective width is around a third of an angstrom or so. And so you're going to need very high resolving power to be able to see any of these very narrow, very intense lines. And my understanding is for a lot of these future missions we've discussed this week, we're discussing them in terms of R value of about 100, resolving power 100, which for our full width half max of this line that we calculated means the spectral element width is about 1,000 times the width of our line. So we're not going to be able to see anything. It's just going to be smeared out and lost. So we have to have high resolving power to view any of these lines that are extremely narrow like this, obviously. So that means we want to have the best planet-star contrast possible. And so this is a plot of the planet-star contrast in colors and contours with resolving power on the y-axis in log scale and our calculated 5577 green auroral power on the x-axis in log scale also. The dashed lines represent the full width half max resolving power in orange and the equivalent width resolving power in the diagonal as it is a function of the power of emission. And so basically you want to have your observation be inside this wedge and with the best planet-star contrast possible. HARPS, for instance, has a resolving power of 115,000, so that's our nominal idea that we need, somewhere in the order of 10 to the 4 to 10 to the 5 resolving power. And if you look at the powers that I just told you on the estimates of our signal, we see that we obtain planet-star contrast of 8 times 10 to the 7 and 7 times 10 to the minus 5 for a direct observation in the optical around for this emission of Proxima Centauri b. So pretty good for a direct observation looking for this emission. But what does this say about the actual integration time you would need? Well, so we calculated the integration time to reach a signal noise of 6 with an R value of 115,000 in all cases. So here on the x-axis, we're looking at integration time in hours, log scale. And we did this for HARPS, HABEX, LUVOIR, and a 30-meter telescope. The green bar is our low end 0.1 terawatt, the yellow bar is 10 terawatt, and then highly unlikely, which I mostly ignore, the 1,000 terawatt emission in red. And so you can see for HARPS, we need somewhere between, in present day, 100,000 to 1 billion hours of integration time. Highly unlikely, we'll say unlikely. But for these future instruments, you can see, especially on the top end here for 10 terawatts, we start getting down to the 10 hour, 1 hour, 0.3 hours of integration time. So this becomes highly probable. And I will say that given the activity, high activity Proxima Centauri, and assuming, of course, that you have a magnetic field, which we've assumed an Earth-strength dipole, an Earth-sized planet, given the fact that if you have a magnetic field, you're likely to drive, a lot of CM activity is going to likely drive substorm activity on the planet through all these assumptions. And you're going to have some signal that's between the two bounds that we have here, this 0.1 terawatt and 10 terawatt. So the average flux that we'll see when we look to Proxima Centauri b, if it has an atmosphere and a magnetic field, it's going to be somewhere between these green and yellow lines. And you look at these future missions and you absolutely see that within a few days, these missions missions and or ground-based scope with a 30 meter could actually pick out these signals within a reasonable amount of time. And so I should have mentioned this at the beginning. LUVOIR, we estimated this for a 16 meter LUVOIR, and this is the 30 meter telescope with a coronagraph of design contrast 10 to the minus 7. Okay, so given what I just told you about HARPS, we did look through the data, and we need at least 100,000 hours, but we have 70. So let's see what we can actually find. So this is a pipeline that we followed for time purposes. I'm not going to go into it too much, but basically we remove the stellar signal, we Doppler shift into the Proxima b's rest frame, and then want to stack all of this flux and look for our 5577. But it's a radial velocity measurement, so we have to be careful about looking through the Earth's atmosphere where we have 5577 airglow and aurora. and the fact that we're looking at Proxima Centauri, which relatively orbits rapidly, and therefore the RV signal will be passing through what we're seeing in overlapping from the Earth. So anytime that one of those overlaps occurs, either from Earth signal with the planet or Proxima Centauri signal with the planet, we remove that data and don't consider it to make sure we're not contaminating. And then we use a filter to get rid of the noise and stack into bins around the line of interest. So here's our strongest signal. We ended up performing a grid search because we had to constrain some orbital parameters of the RV measurement because the inclination is absolutely unknown due to the method used. But our strongest signal came out with an inclination of 52 degrees, this period in mean longitude, and you can see that here. This is in the rest frame of Proxima Centauri b. This is the blue window. You see it down the center here, centered on our line of interest. And then you can see the Earth lines and then the telluric lines from Earth in green and the lines from the host star in red. And again, because we're now in the rest frame of Proxima Centauri b, we see the nice Doppler shift of Earth and the star from that point of view. So since we have all of our flux stacked up, we can just, the flux nicely lined up here for the planet, we can just add all the flux together and look for our signal. We do this, and this is what we see. Here is the signal. There's a bump there, yes. Unfortunately, it's in the middle of a bunch of noise and consistent with the rest of the noise. And when you bin it, the same thing happens. So, and in fact, it is consistent with noise. What we do is we then saw this and took a window of 200 angstroms around to either side of the line of interest and ran this exact same pipeline, the exact same grid search, found the strongest signal for each wavelength in a 200 angstrom window, and we see this. So it's consistent with correlated stellar noise, unfortunately. And we don't expect any emission from the planet on either side of the 5577 line. Yeah, there's a lot of this going on. So we failed to remove all the noise, and that's going to be a limiting factor for seeing these lines at this point, I think, at least with the HARPS data. So the significance is 0.7 sigma, 20% false alarm probability. So we will actually say that absolutely not detection because we don't have the requisite 1 billion hours of data. Okay. But all is not lost. As I mentioned, these future missions have they're enough of a light bucket that they can collect the signal, but we need a high resolution spectrograph to pick these signals out. And so that's part of the hope that we'll see that in the future, that these 10 to the 4, 10 to the 5 spectrographs will be included. We did actually also ran a search for the strong 3917 nitrogen line and the 6300 oxygen line, but also saw nothing. So I told you about our signal strength, which is many times that of Earth. I told you about our expected detectability of making all these assumptions. It requires really high resolving power and a large aperture. We didn't have that large aperture, unfortunately, so we didn't see anything in the data. But we think with future missions, it's likely that we could get some sort of exciting observation like this and constrain the atmosphere directly if we can get all of the technology in place. So thanks to my co-authors and VPL, and thanks to all of you for your attention. I'll take questions.
We have a few minutes for quick questions.
Hi, this is a great effort. So I was wondering, if you stack all the lines together that you have in your spectrum, is that a way to sort of decrease the amount of observing time you need to detect any emission at all?
I'm sorry.
So if you stack multiple lines together, is that a way sort of to decrease the observing time you would need?
I'm not an observer, so that's a really good question. I would refer you to one of my co-authors, and maybe Rodrigo can answer that, yeah.
Do you mean lines of different elements or different lines of oxygen? Absolutely, right? But you want to make sure that you're stacking lines that exist. And so like if you were to stack the oxygen and the nitrogen line, and the nitrogen line doesn't exist, you'll get a lower signal because you're stacking signal with noise. But you can definitely do a search that way where obviously oxygen has tons of lines in the infrared as well, and we could stack all of those and do some kind of grid search. It would definitely increase your signal to noise if you do it properly.
What does the upper limit correspond to in terms of terawatts?
The what? I'm sorry?
You were giving the detectability, you were measuring the line strength in terms of terawatts.
Yes.
And then you presented an upper limit in terms of sigmas. What does that correspond to in terawatts?
Oh, so I believe, the 0.7 sigma, I'm not really sure, but we did run an upper bound of 8 sigma detection, and that ended up being something on the order of 3,000 terawatts or so. But the 0.7 is?
No, it's something ridiculous like that.
Okay.
It's in the paper.
Tens or hundreds of terawatts, yeah.
Let's thank Matt again.